All right, and we're back. Back in another live stream. How long has it been since we've done a live stream before? Today's the 5th of July. Um, and yeah, 13 days ago was when we did our last live stream. Incredible. And we're back. We're back to do some more reading because we finished our Calculus 2 class. And now we only have our object-oriented programming class next. We have some reading. We have a quiz. The quiz is like just 20 minutes. It's pretty easy. And we have a final exam, which is arguably the most important because it's worth a lot of our grade. Yeah, we ended up getting, what was it? An 89, or actually an 86.1 for a calculus class. However, because of the final exam's curve, we ended up with an 89.4. But I ended up dropping that class because I decided to take that class again this fall in ASU to reinforce some calculus skills that are going to be very important for subsequent math classes. Yeah, there's not a lot to say. I think we got a 70 on our final calculus exam. Not the best. I mean, I think I worked very hard, but the result was not the best. That's just the truth. It wasn't like very bad. But it was not the best. I think, yeah, there were 16 questions. I got, what, 12, 11 of them correct? I think I got 5 incorrect, which kind of surprised me because I was pretty confident on them. It might have been just like an algebra error. Yeah. Yeah, I believe we took our final on the 26th. So that was 10 days ago. Or 9 days ago, actually. It was 9 days ago. Nearly 3 weeks. Incredible. Yeah. Yeah, we took our final. Then I went on a road trip. It was a lot of fun, but it was pretty dramatic because our RV broke down. It wasn't cool, but it's okay. And now for this final class, this final section of our class, we have a final exam due on Friday, and then everything else due on Friday as well. What else? Yeah, due on Friday. I think I finished my assignment for this week. I think I just have some reading activities, a quiz, and then our final exam. Yeah, so really we don't have a lot. I just need to focus on finishing everything that I need to do. But that's enough chatting. It's time to get working. Again, since this is the reading, I can't show anything because it'll be deemed as copyright. So you guys will just see me explaining what I understand from the reading. So right now I'm reading about sorting, about algorithms, and the chapter's topic is profiling the selection sort algorithm. I'm not sure what that means, but let's do it. To measure the performance of a program, you could simply run it and use a stopwatch to measure how long it takes. However, most of our programs run very quickly, and it is not easy to time them accurately in this way. Furthermore, when a program takes a noticeable time to run, a certain amount of that time may simply be used for loading the program from disk into memory and displaying the result, for which we should not penalize. Yeah, it makes sense. We don't really know when the sorting algorithm begins doing its job. A lot of it can simply be loading the program, right? Yeah. In order to measure the running time of an algorithm more accurately, we will create a stopwatch class. This class works like a real stopwatch. You can start it, stop it, and read out the elapsed time. The class uses the system.currentTime millis method, which returns the milliseconds that have elapsed since midnight at the start of January 1st, 1970. Of course, you don't care about the absolute number of seconds since this historical moment, but the difference of two such counts give us the number of milliseconds in a given interval, in a given time interval. Here is the code for the stopwatch class together with the class that uses the stopwatch to measure here is the code for the stopwatch class together with the class that uses the stopwatch to measure the sorting algorithm's performance. Note that the timing code in the printed book is slightly different from this interactive version, requiring a separate program run for each array size. Okay, so let's look at our code. We have class selection sort timer. We have our scanner. We print out first array length. We have the variable first length that gets the next integer. In this case, it will be 10,000. Then we print out number of arrays, and then we get 6. So the first array length is 10,000, and the number of arrays is 6. Then we create, what do we create? We create a stopwatch object named timer. We iterate through the number of arrays and n equals whichever iteration we're on multiplied by the length, which is 10,000. Then we construct a random array and then use a stopwatch to time. Okay, I'm wasting time. What am I doing? Gotcha. So we have first array length, number of arrays, length, and then, okay, bro. Yo, I'm crying now. What in the world? Okay. Wait, and what is n? N is, oh, gotcha. I don't know. So 10,000, so it takes 700 milliseconds to process 10,000, to process n, which is 10,000. Gotcha. All right, I think I'm going way too slow. Given the data in the table in the figure, approximately how long would it take to sort an array with 100,000 elements? That's a great question. So with 60,000 arrays, it took 19,000 milliseconds, and a second is 100 milliseconds, I believe. So 700 milliseconds is 7 seconds. So what is 19,000 milliseconds? That would be, if each second is 100 milliseconds, that would be like 190 seconds, I believe. Hold on. Let's Wait. How many milliseconds? Excuse me. Oh, 1,000. Gotcha. So for 60,000 arrays, that is 19 seconds. I think I need to blow my nose. Cool. So this is 19 seconds for 60,000 arrays. Now for 100,000, what would that be? It looks like, I'm guessing. Well, it's obviously above 19 seconds. Between 50. Okay, cool. I'm not sure why that's important, but you gotta do what you gotta do. Given the data in the figure, which of the following formulas gives a reasonable approximation of the execution time t in milliseconds in terms of the array length n? Let's see. Well, obviously we're gonna have n over 1,000. Let's see. What is this squared for? Gotcha. So that's 5.5 times n over 1,000, all of that squared. Would it be cool if they could explain it? Explain why. Unless I'm missing anything, but can it change? Oh, I can change. Yeah, so 6, and then they put 100. Let's see. What do we get? Oh, wait, hold on. What is, wait, so first, oh, that's the array length. Okay. All right. Anyways, given the formula from the preceding exercise, approximately how many minutes would it take to sort an array with 2 million elements? Well, considering n is the number of elements, well, 2 million over 1,000 is 2,000. 2,000 squared, that's like 4 million. 4 million times 5.5, yeah, that's 20 million. T is 20 million. And what in 20 million milliseconds? How much is that? 20 million milliseconds. So 20 million over 1,000. That's like 20,000. That's 20,000 seconds. 20,000 seconds in, I don't know, hours. That's around 5 hours. Gotcha. So I'll put about 6 hours, and that's correct. Okay. Gotcha. Suppose selection sort is timed out on a different computer than the one used in the textbook. Given that n, okay, n is what? N is elements, number of elements. Given that the number of elements is 20,000, given that the number of elements takes time t equals 1.6 thousand milliseconds, and 30,000 elements takes 3,600 milliseconds. Select the most appropriate time t given. Okay, cool. Well, here we multiplied by, well, like 4/3. Well, we didn't even multiply by 2, and this went over 2. So I'm guessing 800, 397, and why would that be? Oh, gotcha. Right, because we divided 20,000 by 2. This should be 1,600 should divide much more than 2. With n equals 40,000. Well, we're obviously going to have that. 50,000 Cool. 60,000. Well, this, right? Yeah. What was the point of that? The code segment below is designed to find the maximum of the elements in an array of integers. Select the expression needed to complete the code segment so that it calculates the running time elapsed. Let's see. Running time is going to be that's a tough one. Well, this one's going to be 0. You can't do that. Is it plus? Oh, I see. Look at a graph in this figure. What mathematical shape does it resemble? What is it asking? Oh, gotcha. A straight line. I mean, not exactly. A parabola. Well, that's like a half parabola. A hyperbola, no, and a sine wave, no. I'll put a parabola. Yeah. The running time increases by roughly the square of the number of inputs. Right. Cool. Yeah, I'm just gonna blow my nose. You know. Alive. So much boogers. Cool. Analyzing the performance of the selection sort algorithm. Okay, I'm gonna open. I feel like I'm going way too slow. So I think I gotta go much faster, obviously. Okay, cool. I don't think we have a lot left. Yo. Cool. Oh. So n is the size of the array. Okay. Okay, cool. Right. Gotcha. So it's n, then n minus 1, then n minus 2, then n minus 3, and like that, all the way until 1. Oh, and yes, and swapping is 2 visits. So we have n plus 2 plus n minus 1 plus 2 plus n minus 2 plus 2 plus n minus 3 plus 2, and like that. And then finally, when you have n minus n, which is 0, so you only end up with plus 2. What are we doing here? We're factoring, okay? Oh, we're grouping, okay. So we have n plus n minus 1 plus n minus 2, all the way like that. That sounds like a factorial. Then we have plus n minus 1 times 2. Hold on, where do we get that? Wait, oh my gosh, dude. What did we do here? Where did we get that? Oh, okay. 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 1 plus 2 plus, okay. Yeah, n times n plus 1 over 2. All right, cool. So the total number of visits that a selection sort algorithm does is n times n plus 1 over 2 minus 1 plus n minus 2, n minus 1 times 2. Gotcha, okay. Gotcha, okay. And what are we canceling now, or? Oh, yeah. Oh, cool. So, yeah, we cancel the 1s, we cancel the 2s. Okay. So we're left with n right there. We're actually left with a bunch of n's. Okay. Oh, so that's n squared. Yeah, 1/2 times n squared plus that would be n over 2. Where did we get the 5? Yeah, where did that 5 come from? Oh, wait, whoops, my bad. Oh, yeah, okay, it's fine. Cool. So number of visits. It's 1/2 n squared plus 5 over 2 times n minus 3. Okay. I think I get that. We obtain a quadratic equation in n. And that's why it looks like a parabola. Yeah, so we only need to look at the 1/2 times n squared. Right. Excuse me. Gotcha. So that's simply n squared. Ah, great. Oh, why 72? So 150 times 500. Okay, so 50. Um, then we have 50 over 2, so that's 25. 75 minus 3, 72. Okay, that makes sense. Um, okay, that's okay. So let's go back to our equation. So 100 squared is 10,000. So 5,000. Um, so we have 500 over 2, 250. 10,000 plus 250, 10,247. Or 5,247. My bad. Okay. Mm, okay. Oh, okay, hold on. So it's this. There you go. Mhm. Oh, there you go. Mhm. What? Oh, wait, whoops. Okay. Mm. Oh, it's only O of 1. Oh, okay. All right, now we have another chapter that requires participation. Let's do it. So now we're going to learn about merge sort. In this section, you will learn about the merge sort algorithm, a much more efficient algorithm than selection sort. The basic idea behind merge sort is very simple. It's a sorting algorithm that first sorts two halves of a data structure and then merges the sorted subarrays together. Suppose we have an array of 10 integers. Let us engage in a bit of wishful thinking and hope that the first half of the array is already perfectly sorted and the second half is too, like this. Now it is simple to merge the two sorted arrays into one sorted array by taking a new element from either the first or the second subarray and choosing the smaller of the elements each time. Right. In fact, you may have performed this merging before if you and a friend had to sort a pile of papers. You and the friend split the pile in half. Each of you sorted your half and then you merged the results together. Cool. This is all well and good, but it doesn't seem to solve the problem for the computer. It still must sort the first and second halves of the array because it can't very well ask a few buddies to pitch in. As it turns out, though, if the computer keeps dividing the array into smaller and smaller subarrays, sorting each half and merging them back together, it carries out dramatically fewer steps than the selection sort requires. Let's write a merge sorter class that implements this idea. When the merge sorter sorts an array, it makes two arrays, each half the size of the original, and sorts them recursively. Then it merges the two sorted arrays together. Gotcha. Um, okay. Suppose the merge method is called, excuse me. Bro. Oh, 5 times. Okay. Okay, cool. Let's do it. Okay. So, okay. And we had 1, 3, and so is 1 less than 2? Yes. So we go to 10. What? Why 18? Oh, okay, right. It just goes out of the if. So now we have 3. Yeah, we have 3. 3 compared with 2. So we go to 13 now. What was it? Which 8? A of 1. Oh, A. Sorry. Equals, so yeah, so we have 2, 8, 9. And what is I sub second? So 2. Value of I second. Mm-hmm. 1. Now 1 and 1. So we're doing 3 and 8. That's obviously true, so we're gonna get 10. What's it, 3? Value of I 2. What is the value of J? 3. After line 6. What is it, 20? So what is I first? I first now is 2. 2 less than 2. No. Now 2 less than 3. That's right. I second is 2. So that's 9. Or is it 8? Hold on. Okay, it's the addition. Wait, I second. Isn't it 3? Oh, 2. Okay. That's 4. So 8. Now 8 plus 9, 17. It's not. Where's it 9? 9. Right. Very good. Okay, I think I understood 92%. Let's go. Let's continue. With an array of length 16, how often is the merge method called? Okay, I think this is going to be length 16. What is it? 4 times, I think. Oh, I only have once in 15. So 15? Oh, really? Oh, gotcha. Okay. All right. We have another one. Oh. Okay. Let's do it. So the merge method is called in lines 1 through 9. 1 all the way to 9 right here. Or execute, which code executes next? Well, let's see. So I first is 0, and first is 0. 0 less than 2, correct. So this one goes first. Next, line 19 executes and the first loop iteration completes. Then lines 7 and 9 execute again. Right, which executes. So now I first was added 1. So we have 24 less than 2. That's obviously false. So this one, correct. So 19 executes in the second loop iteration it completes. Then lines 7 and 9 execute again. So now 24 less than 17. So we go back to this one. Very good. So now we have 20. Wait, which one? That one. So now second is 3. 24 less than 28. Correct. So that one. 30 less than 28. Wrong. So that one. 30 less than 57. Incorrect. 92 less than 57. Incorrect. 92 less than 57. Incorrect. We're cooking. But what happened here? Aren't we at the end of the array? Oh, next line 19 executes. And line 22 executes. Yo, bro, my nose, what's going on? Oh, yeah, I should just have like a paper. Little just. I first lesson first on length. Well, I first. Okay, hold on. Which is lower? Wrong. All right, so line 28. So we need this one. Wait, what? 1, 2, 3, 4. 1, 2, 3, 4, 5. Okay then. Hold on. Wait, but why? First on length is 4. I first is I first 3. I first is 3. Line 26 executes. And line 22 is the while condition true or false? It is false. And that's correct. True? Oh, it's false. Oh, because we also got to the end. Right. I see. Gotcha. Okay. Right. We're almost done with this one. Let's keep going. Okay. So let's see. Oh, okay. Oh. um, okay. All right. Well, that was a lot of fun, but I think I need to go poop. So it was a good time, y'all, but I'll see you later.